So good afternoon. My name is Cawiding. I am a PhD student in biomath, and today we'll be talking about decomposing causality into its synergistic, unique, and redundant components. This paper is from Nature Communications, and as usual, we start with reading the abstract. So, is everyone finished? So, what do you think about this abstract? And can you identify the gap sentence?
Yes.
Could you tell everyone? Yes. So I think it used two sentences to state the gap. So it stated a lot of the problems that current causal inference methods are facing. And even though some of the previous methods address these problems, not all of them can address all these problems at the same time. So we will see how the method here does that. So before going to the main framework of this paper, since some of us are not familiar with what causality is, let's briefly discuss it. So if you're going to Google causality, you will have these two definitions. So it is the relationship between cause and effect, or it is the influence by which one process contributes to the production of another process. So this is the kind of relationship that we want to infer. However, I show these kinds of definition because actually for causality, especially in mathematics, there is no technical definition as compared to other concepts where we can objectively define a certain context. So, but although the definition of causality is not precise, we still have to distinguish causality from other concepts like correlation. So as you can see from this graph, there are two variables. This is the consumption of cheese and civil engineering doctorates awarded. So if you can see the trend, they're very similar. They're both increasing, and the amount of increase is similar all throughout time. However, definitely one variable here cannot cause the other. So that's why it's important that we distinguish these kinds of concepts. So basically, correlation is not causation. But how do we detect causation? In dynamical systems, there's always an underlying dynamics between specific variables. Let's say, for example, here, x affects y, y affects z. But this underlying dynamics is usually unknown, and what we only know is the time series data of these variables. And what current causal inference methods do is that it analyzes these time series data so that it can infer the underlying dynamics. Sometimes it is correct like this, but in other times there are some wrong inferences like this. The current methods are not always accurate. And there are very common scenarios where causal inference fails. And the first one is when there is a presence of the mediator variable, as shown by this diagram. So here, x influences y and y influences z. That is the true underlying relationship, but usually a lot of causal inference methods infer something like this, where x directly affects z. That is one common mistake. Another common scenario is when there is a confounder variable. So in this case, the variable z affects both x and y at the same time. And in this case, since z simultaneously affects x and y, it will appear that the effect in x and y are also simultaneous, so that this is the wrong causality that it detects. And finally, for the last scenario, we have the presence of a collider variable. In this case, x and y both influence z independently, so that means the effect of x is exclusive from the effect of y. But sometimes causal inference methods infer that x and y have a joint influence on z. So these are just some of the common problems of the current methods. And in addition, these methods also cannot account for each of the contributing components of a causality. So for example, here we have the collider variable case. The current methods cannot really tell how much causality is exclusively coming from x or from y. So this is what we call the unique causalities in the context of the paper. And these methods can also not infer how much causality is from the overlap of x and y. These are the redundant causalities. How much from the joint effect of x and y? So these are the effects that can only be observed if you combine the effects of x and y. So these are the synergistic effects. And one main problem also of the current methods is that what if there are some unobserved variables? That means that we don't have the data for this w variable. How is this accounted for? So in this paper, this unobserved effect is called the causality. So in particular, the method here, which is called the synergistic unique redundant decomposition, addresses those questions. So it facilitates the precise identification of interactions by preventing the duplication of causality. So let's take a look at the case where there are two predictor variables, x and y. Usually there is an overlap in the causality of these variables. So that is the blue area there, and this is what we call the redundant causalities. And outside of the blue area, the pink area, this is what we call the unique causalities from x and unique causality from y. And then also, there are also causalities that we can only observe from the synergistic effect of x and y. This is called the synergistic causalities. However, there are also effects from variables that are not observed. I mentioned this earlier, so this is what we call the leak. And so each color here are mutually exclusive. But the total of all these parts is the total information, so that it is equal to the addition of each of the mutually exclusive parts. In this paper, the total information is quantified by what we call entropy. So I think many of us are familiar with entropy, but let's have a recall of what it is. So basically, it is an average measure of uncertainty about the outcome of a random variable. And let's illustrate this by looking at a very simple example. Let's consider the variable x, which represents the event of whether it rains today or not. And this is the formula for the entropy. Let's compare two cases. First case is in the Philippines, and because it is monsoon season right now, the chances of rain is very high. So it rains 90% of the time. However, in Korea, sometimes it rains, sometimes it doesn't rain. So let's say that the probability is 0.5. So we simply plug in these values into the formula for entropy. I think it is straightforward plugging into the formula. And let's look at the final values. So in the case of the Philippines, it's 0.4690, and in South Korea, it is equal to 1. So entropy here means that if the value is higher, then the uncertainty is also higher. So actually, even without looking at this formula, we can say that since the probability of rain in Korea is lower, then the uncertainty is higher. However, in the Philippines, since the chances of rain is higher, then the uncertainty is much lower.
So if probability will be 0.5 in both cases,
then entropy is the same. So the uncertainty is just equal. So is it clear? Is the concept of entropy clear?
Yes.
So there is also one more thing. I forgot to put the effect, but there's also one more thing that we have to learn, which is conditional entropy. And this is the formula. Now we consider another random variable, which is whether to carry an umbrella or not. And yeah, we want to take a look at the conditional entropy. This is just the average uncertainty about one variable once we already know the value of another variable. So in this case, h of y given x is just the uncertainty about whether to carry an umbrella, given that we know whether it rains or not. And actually, the last expression in this formula is just the probability of y given x. So we can think of this equation as just the average uncertainty about bringing an umbrella if we know whether it is raining or not. So we will not solve the example, but given the chances of rain in South Korea and the Philippines, what can we say about, or what can we expect about the uncertainty of bringing an umbrella? Do you know which case will be more uncertain or which case will be less uncertain? So between Philippines and South Korea, Philippines has a higher chance of rain, right? So like intuitively, people will be compelled to bring an umbrella most of the time, right? So there is less uncertainty in bringing an umbrella in the Philippines compared to the uncertainty of bringing an umbrella in South Korea. So that is how it works. So we have to know entropy and conditional entropy because we will also use a concept called the mutual information. So this is how much information is shared between two variables. So we're still looking at these two variables, x and y, and the formula for the mutual information is just this. So entropy of y minus the entropy of y given x. So h of y is just the information about carrying an umbrella, but h of y given x is the information about carrying an umbrella given that we know if it rains. But the difference between this is the mutual information. Intuitively, this measures how much uncertainty is reduced given our knowledge about the rain. Is it clear? So basically, CERD, the main method here, uses the concept of mutual information to decompose the contributions of observed and unobserved variables. So now we are going to look at the general case here, where let's say our predictors are Q1 and Q2. We have the data for this. And our target variable is denoted by Qj plus. So it is a future value of Qj. So that this mutual information, considering these predictors and target, is given by this. So here, the mutual information between the target variable and the predictor variables shows how much uncertainty in the target is decreased given our knowledge about the predictors. H of Qj plus is just the information about the target, and the conditional entropy here is just the information about the target given our knowledge about the predictors. But actually, in the formulation of our problem, what we want is this, or the information, total information about the target. So in CERD, this equation is reformulated as just this, so just rearranging the variables so that the information about the target is just equal to the information from the observed variables represented by the mutual information and the information from unobserved variables. And this is represented by the conditional entropy. So in the case of our diagram earlier, you still remember, this is the total information, this whole figure. And in this step, it is decomposed into the information from the observed variables. So it is this whole thing, the three colors combined, and the information from the unobserved variables, which is the leak. So basically, the leak here is just represented by the conditional entropy of the target given our predictor variable.
Is that J 1 or 2?
Sorry?
Qj, J is 1 or 2?
It can be, but it can also be outside of the predictor set.
So do they consider the past of its own past?
Yes, there is a case where they consider its own past, but there is also a case where they do not consider its own self-causalities.
Is there any reason for such choice?
Actually, I don't know, but in the examples that they showed, they considered the self-causalities, and it's gonna be quantified later. Okay, so far we only the steps only included the decomposition between the observed and unobserved variables. So that part is done, but this thing should still be decomposed into the redundant, unique, and synergistic causalities. And this was done by using the concept of specific mutual information. So for reference, we will keep the definition of the mutual information there. And intuitively, this concept is just the information between the target and the full set of predictors. But the reason they use the specific mutual information is that causality may change depending on the specific state of the target variable. That means we need to compute the mutual information for each of these states. And the way we compute that is through the specific mutual information. And the idea of the computation of this specific mutual information is very easy. So what we do is just consider all the possible subsets of predictors. So in the case that we have only two predictors, one set is just considering Q1, one set is just considering Q2, and the last set is just a combination of Q1 and Q2. And this is just a new notation, but basically the formula is the same. The only change that will happen is that instead of considering the whole set of the target variable, we compute it only for a specific state and get the mutual information together with one of the subsets of the predictors. So intuitively, this is the mutual information between the specific value of a target and a subset of its predictors. So let's take a look at an example. Let's say we have one predictor. Let's say it is the weather. The weather can be cloudy, rainy, or sunny, and the target can be the use of umbrella. And there are some three cases there: no umbrella, transparent umbrella, or a not transparent umbrella. So for mutual information, what it will give us if we compute it in this case is that, on average, how much does knowing the weather reduce my uncertainty about umbrella use? So it's giving you the average uncertainty, whatever the case you consider might be. However, in specific mutual information, we can get some more specific information. So for example, we can ask, or we can answer, how much does knowing the weather help me predict that someone will not use an umbrella? So that is the case where it's cloudy or sunny, right? The case where someone will use a transparent umbrella, of course that is not the case where it is sunny because it cannot block the sun. And lastly, the case where one person will use a non-transparent umbrella. So this can also include the case where it's sunny or rainy, right? So basically this specific mutual information can capture how predictors can influence different types of outcomes of the target differently. And that is the backbone of the decomposition framework here. Now, finally, we will see the schematic of the causal decomposition insert. But I will illustrate this first for the case where there are only two predictors. So the first step is you take a specific state of the target variable and compute all the possible specific mutual information. So it looks something like this. The first bar there is the specific mutual information between that target variable and the predictor Q1. Second one is the SMI between the target variable and the predictor Q2. And finally, this is the SMI between target variable and the full set of predictors. So yeah, you just compute all the possible specific mutual informations, and the next step is just arrange them in increasing order. And finally, not finally, but this is the crucial step. Here we assign which values are redundant, unique, and synergistic causalities. So the first one, the smallest amount of specific mutual information, they interpreted it as the smallest amount that can be shared by all the predictor variables. So, in other words, it is the redundant effect from all the predictors. So this is their notation. So basically, this is the redundant effects from all the predictors, and then we remove the overlap. Since this one already contains the information of 2, we remove that overlap, and what is left is just the information from the predictor variable 1. So this is the unique information from Q1. And finally, the next increment is just the synergistic effect that we can observe from both Q1 and Q2. And since we only computed it for just one state of the target variable, we have to repeat it for all states. So this is the simple version but this was the illustration in the paper. They considered 4 predictors. So there are several cases for the specific mutual information. You have to compute all of it, and then again arrange it in the increasing order, and then assign each increment in order as the redundant, unique, and synergistic causalities. Then repeat it for each possible state of the target variable, so that finally, to get the total redundant causalities, you just get the expectation of all redundant causalities over all events, Qj plus. Same thing with the total unique causalities and the total synergistic causalities. So that is the full framework of CERD. So now, they first tested it on very simple examples. So in the first example, there are 2 predictors and 1 target variable, Q3 plus. And the first scenario where they tested it is in the case where there is a double input, duplicate input. So Q1 and Q2 are just the same, and they tried to solve each of the decompositions. And here we only have a score for R12, so that means it is just the redundant causalities from both 1 and 2. And that's correct because 1 and 2 are just the same. And you can see the leap there. That is just the conditional entropy from the information of the predictors. And the second case is where only Q1 has an effect of Q3 plus. And you can see that the rest, all of the scores are 0 except for the unique causality from Q1. And finally, there's a case where they tested it on Q1 and Q2 having full joint effect to Q3. And you can see here that there's only a score for the synergistic effect from 1 and 2. So these are the simplest cases, but earlier we saw that there are some common scenarios where causal inference methods fail, and they tested it on these examples. So,
could you explain more about why we set the calculated future information in the ascending order, and why it represents the specific, unique, redundant things? Actually, it was not so clear.
So the idea behind that is, so we have this, right?
Yes.
The assumption that they used here is that the smallest amount of causality will come from the overlap of all the causalities.
Okay.
That's why they assign it to the smallest mutual information. And then to remove those redundant defects, they only consider, they remove the overlap information here to get the unique contribution, which will come from this part and this part. And same with the synergistic effect. They remove again the overlap of information here, and this part will be assigned to the synergistic effects.
But in that case, the order could be just random, right? So that part is not so intuitive. So, for example, in the first example, when using only Q2, this is the minimum. Could you go back 2 slides? Yeah, here. So when we use only Q2 information, it gives us the redundant part.
Oh, yes.
Why? So that part is not so intuitive for me. Yeah, I just expected that maybe synergistic makes sense because using both of them could give more information. But why using only Q to give a redundant part?
Actually, you're right, but the only I think that the only information they gave about that is that they assumed that the smallest, as I mentioned earlier, that the smallest causality is the baseline overlap of causalities among all the predictor variables.
Oh,
So they just assumed it, and then they think that if they remove the overlap, then they can just retain which variables are left, and then assign it as the unique ones.
so in the Venn diagram, redundant parts should represent the intersection, right?
Yes.
So they didn't give any some theoretical background on how they calculate.
What do you mean
Yeah, is there any some mathematical formula that to justify that why that portion represent redundant unique? Is that just
Not really. I think they just defined, what they said is that they defined the causalities as increments from redundant, unique, and synergistic causalities. There might be something in the supplementary, but I'm not sure. But in the main paper, that is how they intuitively defined it.
yeah, can move on. Yeah, thank you.
So yeah, let's see the performance on the common scenarios where inference is challenging. So the first example is the case where there is a mediator variable. So here Q3 affects Q2 and Q2 affects Q1. And those are the three equations representing the system. And this was the performance of CERD. And you can see that it's a bit difficult to interpret, but the arrow is, for the first one, for the title, you can see that there is an arrow going to 1. That means that the target is Q1. Here the target is Q2, and this is here the target is Q3. So you can see that for the first case, there is only a unique causality from U2 to U1. So this is from U2, and the target is U1, and that is this relationship. And for the second one, it detected a unique causality from U3 to U2, which is again easily seen from the diagram. If you don't like the diagram, you can just look at the equations, and you can see that Q2 is just in terms of Q3. And finally, there is also, and for the part where we infer the causalities for U3, we can see that only the U3 has a score. There is some small synergistic effect from 1 to 3, but I think they just disregarded it because it is too small. And they also compared it to other methods, like this is Granger causality, conditional transfer entropy, TCM and PCMCI. So basically, these are just conventional methods for inference. And you can see that in Granger causality, it cannot detect the effect from Q3 to Q2. And for CCM, it cannot detect the effects towards Q2 and Q3. similar, the mistake is also similar for the last method, PCMC. In the presence of a confounder variable, here Q3 affects Q1 and Q2 both at the same time. And you can see from the effect, from the performance of CERD that it can detect, so it's easier to see here in my computer, it can detect the unique causality from Q1 to Q1, and this is from the synergistic effect from 1 and 3 to 1. Similar with the case for the target variable Q2, it detects the unique effect from U3 and the synergistic effect from Q2 and Q3. And finally, for Q3, the largest effect comes from its own self-regulation, and the rest are, I think, small enough that they just disregarded. If you check the performance of the other variables, you can see that there are some errors in their detection. I think I'm not gonna point it out one by one, but in this case, CCM and PCMCI fails in the detection of inference going to target 1, 2, and 3. It's the same thing for the case where there is a collider variable. So Ranger causality and CCM both fail in some cases. But so far, actually, we have seen from these three examples that somehow conditional transfer entropy performs the same as CERD. So this is the first case. There are no mistakes. Second case, no mistakes from transfer entropy, and same with the third case. But in the case where there is a redundant collider variable, so what they did here is just equate the inputs from Q2 and Q3, and they both affect Q1. I think this is the case where even conditional transfer entropy fails. But in comparison, yeah, CERD can detect here the redundant information or redundant causality from both Q2 and Q3. So actually, they tested it on many other different systems, but I showed you the cases or the common scenarios where previous causal inference fails. So this is the full set of systems where they try to test these conventional causal inference methods against CERD. And yeah, they claim that in all cases, CERD can detect the accurate causal inference. And actually, that's everything. I think the main points here is that the quantification of CERD decomposes all the causalities into three types: synergistic, unique, and redundant causalities. So actually, for me, this is the first time that I heard these kinds of causalities and this kind of decomposition. And at the same time, it also is the first inference method, I think, that quantifies the contributions of unobserved variables. So the variables for which we don't have the data. And finally, it detects the causalities in cases or in the typical scenarios where the previous inference methods fail. I think these are the three main points of the paper. And that is the end of my presentation.